Welcome everyone to the final stretch of the course. Oh, I'm muted. Welcome to the final stretch of the course. We got 5 lectures left, including this one. And we're done, more or less, with sort of LP solving techniques. We're going to think about duality a little bit today because it applies to the 2 topics we want to cover. But we have all the tools we need to solve LPs. So we're going to start looking at some graph theory algorithms that solve some of the problems we've looked at and a couple problems that we haven't looked at yet, much more quickly than even an LP can solve them. So before we do that, I just wanted to point out that homework is due tonight. I have office hours tonight, and the spot surveys have opened. So that gives you a chance to give feedback on my teaching and the class in general. And I really, really want everyone to do that because teaching is something that I want to get good at. It's something I'm very new to, and I'd really appreciate any feedback that anyone can give me. And I know it's been a fast-paced and a little bit of a dry course, but feedback is important to me. So please fill out those spot reports. That's it on that front. So let's look at some network problems. So in the book, very early in the book, we talked about graph theory, what graphs are, and specifically 2 problems, the shortest path problem and the perfect matching problem. And we mentioned, or I mentioned, that especially the shortest path problem can be represented as an LP or an IP, I suppose. But it's big and it's actually hard to solve as an LP in general. But I also mentioned that there exist algorithms from graph theory that solve these things very quickly. So we're going to explore one of those algorithms first, and then we're going to talk about a new class of problem that we haven't mentioned before. So remember the shortest path problem. I forgot to turn on this. Suppose we have a graph. And we want to find the shortest path from the S node to the T node. S is usually called the source. T is called the sink or the terminal. Sink is more common. I tend to like terminal because it's T. But we want to find the set of edges that will take us from S to T in the shortest distance, shortest number of edges. So if they're unweighted, like this, that's not the right one. If they're unweighted edges, we might pick these 3 edges. I don't see a shorter path in this graph. But we also could have weights on our edges. Maybe this is 10, 5, 7. Maybe this is 4, 3, 1. Let's say 10, 5 again. Well, if we have those weights, the shortest path is not the minimum number of edges, but it's the minimum total weight, which is this path. That's the goal of the shortest path problem. Yeah, and you may remember that we came up with a IP model here for this. So let this graph be G with vertices and edges, and some weights, C, E, for every edge. Weights or costs or distances, what have you. This is the problem that Google Maps solves every time you want it to navigate you somewhere. A variety of other problems, other examples. Yeah. So we modeled this as an IP. We want to minimize the sum of CE XE such that this is for all E in E. The sum of E in Q times XE is greater than or equal to 1 for all ST cuts Q. Or maybe better, for every ST cut. Oh. And then XE is binary. For every edge. This is the model we came up with, and that's presented in the book. We did this by saying that a cut is just a set of edges that any path from S to T must pass through. And if we can identify all of those cuts, we can make this constraint. You can simplify a little bit. You can ask for minimal cuts. But still, there are potentially very, very many of these cuts in a given graph. I think I said there were something on the order of 2 to the E, 2 to the number of edges cuts in a given graph, which is very, very many, and we'll talk more about what that notation means in DOR2 if you take that, and we'll talk about it in a computer programming class. But basically it means that the problem, the LP, is much, much bigger than the graph itself, if that makes any sense. The graph may not be massive, but the LP that's representing the shortest path problem could be massive, and it could be take a long time to solve. So we mentioned so there are this many cuts and this many constraints. Um, so I mentioned that there are a few non-IP algorithms that are useful in solving this problem. The book presents one. Um, it's an uncommon. It's one I haven't seen too many other places. I like it because it uses the dual to justify itself, um, but it's not the most common per se. So instead of the one in the book, I think that's section 4.3.1, I believe. Yeah, 3.1.4. They present a shortest path algorithm. That is a slight, it's more sophisticated than what we're going to do, but it's also not as common and not as informative, I think. So the one we're going to do, that's a spare slide. We're going to talk about Dijkstra's algorithm, or Dijkstra's algorithm. I'm not positive how it's pronounced. This is sort of the path of the algorithm, or it's the pseudocode. It's the set of instructions that we're going to follow to find the shortest path. So if we have a graph with vertices and edges and edge weights, then we're going to find the shortest path. So the first thing we're going to do is we're going to assign a tentative distance to every vertex, and we're going to let that be infinity to start out with. We're going to assign a prior visit to every vertex, and then we're just going to leave that empty for now. We're going to assign, this should be U, not V. We're going to define a set of vertices that we haven't visited yet. We're going to call it U, and at the beginning, we're just going to set it to the full set of vertices, because we haven't visited any of them yet. And then we're going to mark S as current, and we're going to call that R in our iteration. So then we have a while loop, which just says at the end of every iteration, we're going to check is our terminal, still in U? Is it still unvisited? If that's true, we're going to do another iteration. If it's not, then we stop. We're done. So then, for every unvisited vertex adjacent to R, to our current vertex, we want to decide is it faster to go from the start to our current vertex and then to U, or is it faster to go the direction that we already identified earlier? And we'll do an example of this, and I'll explain what all of this jargon is in an example setting. So if it is faster to come from S to our current vertex R and then to U, then we're going to set the new tentative distance to u. This should be dr plus c ru. So dr is the tentative distance of our current vertex, and cru is the distance associated with that edge between r and u, because they're meant to be adjacent. And if that is less than the current tentative distance of u, then it would be faster. It would be a shorter path to take edge ru. So we set this new tentative distance, and we set the prior of u to r, to the current vertex. And then once we do that for all the neighbors of r, we're going to remove r from the unvisited set. And then we're going to mark the vertex in the unvisited set with the new smallest tentative distance, the new smallest d value, as current. And then we're going to perform our while loop again. And then once we find an iteration where t has left, where it has been visited, it is no longer in the unvisited set, we're done. We terminate our while loop, and then we follow the prior visit set back to s, from t to s, to find the shortest path. So let's demonstrate this on this example. We want to go from A to G. So A is our start, and G is our terminal, our source and our terminal. So the first thing we do is assign a sort of, what was it? Yeah, we assign a tentative distance of infinity to every vertex. It's infinity because we haven't found a path there yet. We're going to set the tentative distance of A to 0 because we're starting at A. So y so we already do know a path from A to A, is what I'm saying. And then so our unvisited u is everything, A, B, C, D, E, F, G. Our prior visits is just going to be empty for now. But I'm going to go ahead and mark the locations of everything, where everything's going to go. And then our tentative distances, I'm going to bring down here. Well, let me do that differently. I'm going to say our current I'm going to make a table. Yeah. So this is the current vertex for a given iteration. So we're going to start at A, and then we're going to have the distances in this side. So that's going to be A, B, C, D, E, F, G. A to A is 0. And everything else is infinity for now. So A doesn't have a prior. Because it's the start. So you could leave that out of P if you wanted to. Then what we want to do is find, so we have two vertices that are adjacent to A. A has two edges leading out of it. They lead to B and C, so B and C are adjacent to A. The distance from A to B, well actually let's copy all of this, bring it on a new page. There we go. So the tentative distance to B is 2, because we have a distance, or the edge weight of that edge is just 2. And the weight of the edge from A to C is 6. So we update tentative distances. 2 is obviously less than infinity, so we make that update. 6 still less than infinity. So we make that. And then we have to remember to update the prior as well. Let's do the distances first. A to B is 2. C is now 6. And we haven't touched any of the other things yet. The prior of B is A, and the prior of C is currently A. And then we take A out of the unvisited set. I like to mark the edges that I've used. Well, I like to mark out the priors, the prior edges, because we'll see that it ends up showing us our shortest path there at the end. So when I'm doing this by hand, I like to highlight the edges that are currently in the prior list. Then, whoops. So let's do this again. Now, what we have to do is pick a new R. It should be the set of unvisited. It should be the unvisited vertex with smallest tentative distance. B is unvisited. Its distance is 2. That's smaller than 6. So B is now current. Then we look at the set of unvisited vertices that are adjacent to B. That's going to be D. The new tentative distance to D is 2 plus 5 is 7. 7 is smaller than infinity. So the new distance is 7. A has already been visited. We don't need to update it. B is current. We don't need to update it. C is not adjacent. We can't update it. D is now 7. Everything else is still infinity. And the prior from D is B. So I'm going to highlight that edge. Then B has been visited, so we mark it out of the unvisited set. Let's do it again. So we pick a new current, smallest distance unvisited vertex. It's going to be C or D. C is smaller. So we look at C next. It's only adjacent to D, but it wants to say 6 plus 8 is 14. 14 is bigger than 7, so we don't update that tentative distance or the prior because A to C to D is longer than A to B to D. So we don't do anything here. Well, we should continue to update our table, but none of our distances change, and none of our priors change. So we did also visit C. I should mention that. So we mark him out. Now D is the only unvisited vertex that has any has a finite tentative distance. So D is our new current. It's adjacent to E. So 7 plus 10 is 17 is less than infinity. So we update that. D is the prior of E. 7 plus 15 is 22. So we update the distance to F like that. G is still out of touch. It's still infinity. And we mark down that we have visited D. And move ahead to another iteration. We still haven't visited G, so we're still not done. Oh, I also should have highlighted those priors. Yeah, okay. This slide. want to highlight this edge and this edge because they're in our prior list. Then we do it again. We pick a new current. It's going to be either E or F. E has a smaller tentative distance, so we pick E. Most of our stuff is unchanged. 0, 2, 6, 7, 17. F, we can now get to 17 plus 6. You know what I'm going to do on the fly here to demonstrate this better? I'm going to change that to not 6 but 3. I want that edge to be 3. So 17 plus 3 is 20. Oh, I've neglected to update it on here, didn't I? This should have been 17 and 22. The same on... No? Oh. Whoops. Working on the wrong slide. Here we go. Yep. So 17 and 22. And this is now 3 instead of 6. So we picked E as our current. 17 plus 3 is 20, is less than 22. So we are going to update F to 20. Its new prior is E. So we're going to erase that highlighted edge. Now this edge is in the prior. And 17 plus 2 is 19. So G is 19, and the prior is F. E. And now we have visited E. So we're getting close here. So now we pick our new current. And we see that F and G are unvisited still. G has a smaller value of 19. Oh, I didn't update this. Or this. Yep. G has a smaller value of 19. So we're going to pick G as our new current. Oh, we also should have highlighted this edge. So G it's only adjacent to F. 19 plus 6 is 25, is much bigger than 20, which F is currently at, so we don't touch it. That's the only thing it's adjacent to, so nothing is updated in our shortest path. So Dijkstra's algorithm, so we're done because we've just marked G out of the unvisited, and our while loop is complete. Do I have another slide here? Yeah. Let's copy this one more time. So we're done. We got to G. And now all we have to do is look at our tentative distance is the length of the path, and the prior gives us the path itself. So if we start at G and look back, G came from E, so E to G. E came from D, D came from B, B came from A. Which is G to E, E to D, D to B, and B to A. Is our shortest path. And if we sum up everything, we have 2 plus 5 is 7, plus 10 is 17, plus 2 is 19. That matches up with our tentative distance for G. So we found the shortest path. In fact, in this case, we have found what's called a minimal spanning tree for this graph, which we'll talk about tomorrow. The minimal spanning tree is another type of problem that is related to the shortest path, but Dijkstra's algorithm can be used for both of those problems, which is neat. So the idea of Dijkstra's algorithm is that every part of a shortest path should also be a shortest path. So if we had wanted to start originally from D to G, if we'd wanted to find that shortest path, we would still be finding the red highlighted path. That is already a shortest path. So the idea is once we've found a shortest path partway through the graph, we don't have to think about the rest of it. Well, we don't have to think about that part of the graph anymore. We can just look forward to the rest of it, which is a neat proposition. The algorithm in the book, I said it earlier, 314, is slightly more sophisticated. It uses the idea of the dual, and that the dual is looking for cuts to um, to identify which edge is going to end up being in the shortest path. So it does not search the whole graph. It does not find a tree, a minimal spanning tree, like Dijkstra's algorithm does. It only finds a path, which is very cool, and it's neat that it uses duality to do that. But it's not a common algorithm. I don't think Dijkstra's is much more popular. I'm not even sure what that algorithm in the book is named. So that's that. That's how we solve a shortest path problem. And I said earlier that the LP was order to the number of edges. I'm trying to, what's the complexity of Dijkstra's algorithm? That is order number of vertices squared. Which we'll talk about exactly what that means in DOR2 in not very much time, for those of you who are going to be in that class. But this is much smaller. This is what we call a polynomial time algorithm, whereas the LP has the potential to be an exponential time algorithm, which takes a lot more time. So, if you're doing a problem, a word problem, that sounds like it should be an LP, but that you can make it work as a shortest path problem, there are faster ways to solve it than using an LP, especially if it's a big problem. Use the shortest path if it's available. So the next problem, so that's shortest path, that's how we solve that. The next type of problem is related. And it has a very, I think, very, very interesting theorem attached to it, and very important for the solving of this type of problem. So I thought the book had a good example. Suppose you are trying to video chat with someone, like we're doing now over Zoom, and you want to bounce your signal, your broadcast, through several routers in your network of routers. And each router only has a certain bandwidth that it is sending to its neighboring router or server or whatever. I'm not a computer engineer. I don't know the precise terms to use. I think server is probably better. So each server is going to be a node. Again, we're going to start at A and end at G. Nodes are servers. Edges are bandwidth. Between servers, and you want to maximize your bandwidth from A to G. We're going to send, we want to send our signal between these servers in such a way that we have the most bandwidth possible. We have the highest quality of signal coming through. And we can use as many of these servers to do that as we want, or as capacity allows. This is called a flow problem. It's useful in transportation type problems, distribution type problems. If you're, we talked about computer networks. If you're wanting to get as much of your product that you're producing from your factory to a certain location, you're going to want to think about a flow problem. Very common problem. So the question is, how much flow can we send from A to G? And flow is just the sort of generalization of the bandwidth idea, or the amount of product idea. And each edge, instead of a cost on that edge, that number is now a capacity. That's how much flow can that edge, that server connection, that sewer pipe, how much can it handle? And interestingly, this problem is almost always done on directed graphs. So you may be able to see the arrowheads that I have added to this graph to each of the edges. And that just indicates that that edge only flows in one direction. We call that a directed edge, or an arc. And the graph is often called a directed graph or a digraph, in case you hear any of those terms out in the wild. So we can model this as an LP. Let XE indicate the flow that we send across each edge, E. And what we want to do, G is our terminal, and A is our is our source. We want to maximize the amount of flow running into G, running into the terminal. So this delta plus, recall that delta at one point of an edge, or of a vertex, is the edge, set of edges incident to V. Delta, not D, but delta plus, we use on directed graphs, is the set of edges running into V. So if the arrowhead points towards vertex V, that edge is in delta plus. Similarly, delta minus is a set of edges running out of V. So just as an example, these two edges are in delta minus A, but delta plus A is the empty set. It's empty. It doesn't have any edges. This edge is delta plus F, and these two edges are delta minus F. So what we want to do is sum the amount of flow heading into the terminal T. So for every edge running into T, or in our case G, we want to maximize the flow over those edges. That's our objective. Our constraint says for any vertex, actually this should be excluding S and T, or A and G in our case. For any vertex except the source and the terminal, the flow into that that vertex should equal the flow out of that vertex. It's called flow balance constraint, and it just means that we don't have flow getting lost in vertices. There are generalizations of this problem where you might want to let that happen, but the algorithm I'm going to present doesn't allow that. And then we just have that the flow over any edge is less than the capacity of that edge. So let me present that again. We're maximizing the flow into T for vertex except S or T. The flow into that vertex equals the flow out. The flow over every edge is less than or equal to the capacity of that edge, and the flow is positive. So the book has a really crunchy theoretical way of showing this theorem. I'm not going to do that because it is somewhat complicated. The dual can be thought of sort of like this. The book has a nice way of explaining it, I think. So if you're interested in it, look at that section again on maximum flow min-cut theorem. But the dual kind of, in general, looks like this. Minimize the total capacity of selected edges such that the selected edges form an ST cut. And what that means is we want to select edges let's use these two edges such that every flow has to use one of those two edges, or one of the however many you picked edges. Now, trivially, we could every edge that would be a valid ST cut, because then if you remove those edges, there's no way to get from A to G. There's no path from A to G. But that's not interesting. If we remember, the primal problem is a maximize flow, and the dual is find a minimum cut. And we know by the duality theorems that they should be equal. They should have equivalent objective function values, which is really it's really neat to be able to prove that mathematically, and on this plot we'll see that it's sort of easy to see with this graph. It's an easy thing to identify, but it's neat that duality kind of proves that here. And the book has an explanation of what is it talks about totally unimodular matrices. I don't want to get into that until DOR2, but just know that this class of problem, this maximum flow problem, and by extension the minimum cut problem, will always return an integer solution if you use the simplex algorithm. It always has an optimal integer solution. So if you're doing a maximum flow problem, you do not need to worry about enforcing integer constraints on your solver implementation. It's always going to find an integer solution, which is really neat and really helpful. And it's actually the crux of the proof in the book is about totally unimodular matrices. We'll talk about that in DOR2. I keep saying that, but it's true. What I want to show here is that the cut I just selected, it has a capacity of 11. So we found one that has a capacity of 11. But there are more cuts here. We could pick these two. That has a capacity of 8. Obviously, those are the only two edges flowing into G, which is our terminal. So the capacity of those two edges is going to bottleneck the capacity of the flow in general. And in fact, that is one of the two minimal cuts. You could also pick these two edges. That is also a minimal cut. So our flow is going to be capped at 8. The Ford-Fulkerson algorithm is the algorithm that is used to solve this problem. So given a directed graph with edge capacity CE, and CE has to be non-negative for this to work properly. The following algorithm determines the maximum flow between vertices S and T. And in fact, if we add a little bit more to this, it will also find the minimal cut. The maximal flow informs the minimal cut. And we'll see that depending on how far we get with this algorithm. The idea is that we're going to find a path from P to, or from S to T, and we can do that using a depth first search, or there are varieties of ways to find just a path. It does not have to be a shortest path. In fact, if you ask for shortest paths, the algorithm is not going to finish to completion. And I'll explain what this means. They either have to be, all of the edges in that path either have to be forward facing with spare capacity or backwards facing with spare flow. And we'll show what that means in a little bit. And then you need to identify the minimum of the capacity, the spare capacity of each forward-facing edge, or the spare flow of the backwards-facing edge, and then add that much flow to P, or subtract it from a backwards-facing edge. And this ends when no suitable path can be found. So I was going to do it on the problem we just did, but I don't really. I have another example that is a little more in depth that I want to start with. So, sure, first thing we need to do is find a path from S to T. I like this path. Nice and easy to see. We're noticing that we're taking directed edges and we're following the direction of those edges all the way to T. And we haven't sent any flow over these edges yet, so they all have some spare capacity. And then I find the minimum of that capacity. We have 10, 4, and 10. So I'm going to send 4 flow over this path. So 4 out of 10, 4 out of 4, and 4 out of 10 is sent this way. So this top edge is used to its full capacity, but these other two are not yet. So 4, 4, and 4 out of 10. Next, we need to find another path. This path we cannot use A to B because it has full, its capacity is full. So instead, I want, and the order that you pick these paths in does not matter. This will terminate eventually. I want to follow this path. Again, we're in the direction that the edges call for, and we have spare capacity everywhere. And now we want to find the minimum of the spare capacity. This has 10 minus 4 is 6. This one has 8 spare, 6 spare, and 6 spare again. So we're going to send 6 more over these edges. So 6 plus 4 is 10 out of 10, 6 out of 8, 6 out of 6, and 10 out of 10. So some of those are now used at capacity. Oh, so this had a capacity of 6 before we used it. This had a capacity of 4. So let's do another iteration. We can't use S to A because it's at full capacity. So we're going to have to start using S to C. And then, yeah, let's use C to D and D to T. This has a capacity of 9. 9 is the smallest capacity, the spare capacity on this path. So we get 9 out of 10 everywhere. So, now we look for a new augmenting path, is what it's called. And we notice that there's actually a cut here. These three edges form a cut, an ST cut. They're all used at capacity. Any flow, any path from S to T has to use that cut. It has to use one of the edges in that cut. But all of those edges are used at capacity, so we can't add any flow to them, which means that we're full. We're using everything we have. And we can notice that the capacity of that cut is actually 4. Actually, they're not used to capacity. What am I saying? No, they're not used to capacity, because this one still has a spare. But look at it this way. 4 plus 6 is 10, plus 9 is 19. Huh. There's something screwy here. But there's also 19 flowing into T. This is weird, because it's not used at capacity for some reason. Give me a moment. Let me find where this example came from. No, they have the same solution. Huh. I thought that was the minimal cut. It's not. Where is the minimal cut? This is the optimal flow, but I'm confused where the minimal cut is. Because that cut has a capacity actually of 20, which is one higher than the flow we're getting. This is also a 20 capacity cut. This is odd. I might have to investigate this on my own between lectures because we are out of time. I will stick around and look at this for a little while and answer questions, but you guys are free to go.